You know, when you think about using a computer or really any software over the past few decades, there's this deeply ingrained rhythm that you and I just instinctively share.
Right, it's totally second
Ah,
nature at this point.
exactly. You reach for the mouse, you click a menu, a drop down appears, you click an option, and the machine obeys. It's entirely reliant on you driving the action.
You're the one in control.
Yeah, I mean, think about driving a manual transmission car. You have to understand the clutch, the gear shifts, the RPMs. You are micromanaging the machine's internal state just to get down the road.
Yeah, you're doing all the heavy cognitive lifting.
But suddenly, we are looking at a software landscape that is essentially dropping us into the back seat of a fully autonomous vehicle. You just state your destination, and the machine figures out the route, the speed, the traffic, and the steering. We are witnessing the total inversion of what it means to, use a computer.
It really is a radical transfer of cognitive load.
Hmm.
Historically, human beings have had to translate our high-level goals into the low-level, step-by-step syntax that a machine can understand. But now, the systems are acquiring the capacity to do that translation themselves.
And that is exactly what we are getting into today. We are moving from static, waiting to be clicked software to proactive autonomous systems.
hmm
To really anchor this, we are basing our entire conversation on this incredible architectural breakdown called the Orchestrator's Blueprint, Architecting the Generative Agent Ecosystem.
It's a dense read, but totally fascinating.
Oh, absolutely. And our mission for this deep dive is to completely demystify this blueprint for you. We're going to extract the most vital insights about how multi-agent intelligence actually works mechanically and what it means for how you will interact with your digital life moving forward. Okay, let's unpack this.
Let's do it.
Starting with the most massive conceptual hurdle, the paradigm shift from deterministic UI to agentic UX.
Yet to understand where we are going, you have to look at the structural limitations of where we are. So
Mhm.
deterministic user interfaces, they're built on rigidity.
Right.
Deterministic literally means predetermined. The software developer has to anticipate every single thing you might possibly want to do and build a literal hard-coded pathway for it.
Right. So if you open a traditional application, you have a main menu, you click File, which opens a pathway to export, which opens a pathway to PDF. It is a linear chain of events.
Exactly, linear.
And crucially, if the developer didn't hard-code a button for export to PDF, you simply cannot do it. The system is completely blind and paralyzed outside of its pre-programmed pathways. It just sits there, burning electricity, waiting for you to click.
Right, you are trapped within the imagination of the original developer.
Mhm.
But contrast this with agentic user experience. In this paradigm, those menus and submenus, they just dissolve entirely.
They're gone.
Gone. Instead, you have what's conceptually called a central goal node. You, the user, simply define the destination.
I love thinking about it like this. Deterministic UI is like ordering from a rigid fast food menu. You walk up to the cashier and you have to specify every single variable. I want a number 4, no pickles, extra ketchup, medium fried, diet drink.
Right, you have to spell it all out.
Yeah, you make every micro decision to orchestrate the exact output. If you forget to say no pickles, you get pickles because the cashier isn't authorized to anticipate your preferences.
They're just following the deterministic script.
Exactly. But agentic UX is like having a world-class personal chef. You walk into the kitchen and just say, I'm hungry for something healthy that uses the vegetables we bought yesterday. And then you leave the room.
You literally walk away.
Yeah. The chef takes that vague intent, figures out the recipe, controls the heat, times the courses, and plates the dish. You just get the final outcome.
The mechanical difference there is profound. The personal chef possesses domain expertise and autonomous reasoning.
Hmm.
In the software equivalent, when you set that central goal node, the system dynamically spins up a web of interconnected tasks.
It builds the menu on the fly.
Yes, it might realize it needs to spawn a data analysis task, which then feeds into a pattern recognition task, which then branches out to allocate resources. And those separate internal processes communicate with each other, looping back and forth until they converge on a solution. You didn't tell it how to analyze the data or where to find the resources.
You just wanted the meal.
Exactly.
So to map out how we're actually getting from the fast food cashier to the personal chef, there is a fascinating framework in the blueprint that tracks this evolution across an intelligence spectrum. It breaks down into 4 distinct columns. Let's look at the first one. RPA, or robotic process automation. We've had this in the corporate world for a while.
We have, and it's important to understand its limitations.
Hmm.
RPA is characterized as repetitive and rule-based. Its internal logic is entirely deterministic if-then.
Okay, give me an example.
So you might write an RPA script that says, if an email arrives with an invoice attached, download the PDF and save it to the accounting folder.
Which sounds great because there's no human needed for that specific loop.
It is great for that one exact scenario, but there is absolutely zero AI planning involved. It is brittle.
Brittle how?
Well, if a vendor sends an invoice but puts the link in the body of the email instead of as an attachment, the RPA script crashes.
Oh, because the if condition wasn't met exactly.
Right. It has no ability to reason about the intent of the email. It only looks for the explicit trigger it was programmed to find.
Which leads us to the second column on the spectrum, basic LLMs, large language models. This is the ChatGPT interface that kind of shocked the world recently.
Yeah, and this represents a fundamental break from deterministic logic to probabilistic logic. An LLM doesn't follow an if-then path. It generates text by calculating the probability of the next word based on massive data sets.
But wait, if it's probabilistic, isn't it basically just guessing? I mean, how is that better than a rigid rule?
It's better because it can handle ambiguity.
Oh.
If you ask an LLM a question in broken English, or ask it to summarize a messy, unstructured document, it can probabilistically derive the meaning and give you an answer. An RPA script would just fail.
It would just crash, like you said.
Exactly. However, the basic LLM has incredibly low autonomy. You still have to prompt it at every single step. If you ask it to plan a marketing campaign, it will output a beautiful text document describing a marketing campaign.
But it can't actually do the campaign.
No. It cannot actually email your team, buy the ad space, or monitor the analytics. It just generates text. You, the human, are still manually executing the plan.
Which brings us to the third column, co-pilots. This is where a lot of enterprise software is living right now. The autonomy level steps up a bit. It's task-oriented.
Yeah, the logic here is suggestive. A co-pilot is contextually aware of what you are doing. If you are writing code, it analyzes the lines above and suggests the next block. If you are drafting a spreadsheet, it suggests the formula.
Right. But crucially, the human is still making the final decision. You have to hit the tab key to accept the code. The co-pilot is in the passenger seat with a map, but your hands are still firmly on the steering wheel.
That's a perfect way to put it.
And that finally brings us to the glowing center of this whole architectural shift, column 4, AI agents.
If we connect this to the bigger picture, this is the Rubicon that the software industry is crossing right now. The autonomy level jumps to high. The logic becomes dynamic reasoning and action.
So it's not just suggesting anymore?
No, this isn't just suggesting the next word. This is the system reasoning about a multi-step problem and taking independent actions in a digital environment to solve it.
The structural shift in the human's role here is wild. The framework describes the human as being moved to the perimeter for oversight. You aren't driving the car anymore. You are essentially an air traffic controller.
Right.
You're watching the radar blips to ensure the planes are generally behaving, but you're not in the cockpit flying them.
Because the system is now capable of deep, multi-step orchestration. It can encounter a sub-problem, realize it needs more information, go find that information and resume the original task without stopping to ask you for permission or a new prompt.
Wow. Bill Gates actually summarized the gravity of this perfectly in the source material. He said, in the computing industry, we talk about platforms, Android, iOS, and Windows. Agents will be the next platform.
That's a huge statement. To call it a platform means it becomes the foundational layer. Windows is a platform because it mediates between your hardware and your software. You don't have to tell your graphics card how to render a pixel.
Right, Windows handles that.
Exactly. Agents will mediate between you and the entire digital universe. You won't open a specific travel app to book a flight and a separate hotel app to book a room. You will just tell your agent your travel intent, and the agent will interact with the underlying APIs of those services on your behalf.
So the traditional application interfaces will largely become invisible.
Mostly, yes.
Okay, so if the interface is disappearing and these agents are going to be acting as our personal chefs and travel coordinators, we have to look under the hood. How does a piece of software actually think well enough to do this? If it's operating autonomously, it needs like an internal architecture.
It does. We have to look at the anatomy of an agent. It starts with how the system perceives the world, which is simply an input node.
Okay.
This could be a text prompt from you, but it could also be a data stream from a stock ticker, an alert from an inbox, or a sensor reading. It takes in this perception and feeds it into its central cognitive hub, the memory systems.
Let's talk about memory because I think a lot of people assume an AI just has a giant hard drive. But structurally, the memory of an autonomous agent is partitioned into four highly specific quadrants. The first is short-term memory, which handles the immediate context.
Mechanically, short-term memory is constrained by what we call the context window.
Yeah.
When you are talking to an agent, it needs to hold the recent parameters of the conversation in its active processing space.
Give me an example of that.
Well, if you say, draft an email to Sarah about the budget, it holds Sarah and budget in its short-term memory. But this space is finite. If the conversation goes on for hours, the earliest details get pushed out of the context window.
Oh, interesting.
It's exactly like human working memory. It's fleeting and highly focused on the immediate task.
Which is why the second quadrant is so vital. Episodic memory. This stores past specific events, right?
Right. Let's say you tell the agent today, whenever you draft a budget email, I prefer it to be heavily bulleted in under 2 paragraphs. That preference gets saved outside the temporary context window into a long-term storage retrieval system.
Okay, so it actually remembers for next time.
Exactly. 6 months from now, when you ask it to email Sarah about a new budget, it dynamically queries its episodic memory, retrieves that specific behavioral preference, and injects it back into its short-term working memory before it writes a single word.
That is how it builds a persistent relationship with you over time. That's incredible. Then we have the third quadrant, semantic memory. This is the general world knowledge.
Yeah, semantic memory is the foundational intelligence baked into the model's neural network weights during its initial training. It's the vast corpus of human knowledge.
Like reading the whole internet.
Pretty much. It's how the agent knows the rules of English grammar, the capital of France, and the syntax of the Python programming language. It is the broad encyclopedia it uses to comprehend the world.
Okay, and the final quadrant is procedural memory, which the blueprint defines as learned skills.
This one is crucial. Semantic memory knows what a database is. Procedural memory is the specific executable skill of how to write the SQL query to extract data from your company's specific proprietary database. It is the repository of tool use scripts.
Okay, wait, I have to push back a little here. Looking at these four memory types, short-term, episodic, semantic, procedural, it sounds incredibly comprehensive, but isn't this just a perfectly organized database?
What do you mean?
Well, my laptop has a hard drive with my past events and general knowledge. If this memory system is just storing information, how does the agent actually initiate action? How does memory translate into, momentum?
That is the exact friction point of the whole architecture. Memory is static. To create momentum, the memory systems feed directly into a core processing unit called the planning node.
Okay, the planning node.
Specifically, it's engineered for task planning and tool usage, or TPTU, as it's sometimes abbreviated.
So the planning node acts as the engine.
Precisely. We have this quote from Harrison Chase that illuminates this perfectly. An LLM at the center deciding the control flow of an application. Think about how radical that is.
Because usually the developer does that.
Exactly. In the past, the developer wrote the control flow. The code said, first do A, then do B, then do C. But in this architecture, the LLM itself is the router. It takes your input, queries its 4 memory quadrants, and dynamically formulates a strategic plan on the fly.
It figures out the steps itself.
Yes. It decides, based on this goal, I need to perform step A, which will give me the data to perform step B.
It's reasoning about the sequencing of events. And to understand just how complex that reasoning can get, the architectural blueprints lay out an agent taxonomy matrix. It categorizes these digital minds by their level of sophistication.
Right, because not all agents require the same cognitive weight. Just as biological life scales from simple reflexes to deep cognitive reasoning, digital agents scale based on their internal state and decision logic.
Let's walk down this taxonomy, starting at the absolute bottom. The simplest form is the simple reflex agent.
The decision logic here is completely predefined. If X happens, do Y. Think of a digital thermostat.
Classic example.
Right. It has no memory of yesterday's weather. It has no plan for tomorrow. It simply checks its current input, the temperature, and if it drops below 68 degrees, it triggers the heater. Its adaptability is completely rigid.
A very useful but totally reactive system. One step up from that is the model-based agent.
This introduces a critical capability, maintaining an internal state of unseen elements.
Unseen elements.
Yeah, think of an early algorithm for a robotic vacuum cleaner. It bumps into a wall, turns, and moves forward. But crucially, it remembers that the wall is behind it, even though its sensors are no longer looking at it.
Ah, okay.
It is building a rudimentary internal model of its environment, to predict outcomes.
That makes sense. Then we escalate to the goal-based agent.
Now we introduce proactive search and planning. A goal-based agent doesn't just react to its environment. It has a defined objective.
Hmm.
If you put a massive roadblock in front of a model-based agent, it might just bounce off it indefinitely.
Like the vacuum cleaner stuck in a corner.
Exactly. A goal-based agent detects the roadblock, realizes its current path is blocked, and actively calculates an entirely new route to reach the destination.
Here's where it gets really interesting, though, because reaching the goal isn't always enough. The next level down is the utility-based agent.
This is a massive leap in sophistication. A goal-based agent simply wants to reach the destination, regardless of how chaotic the journey is. A utility-based agent balances competing factors. It evaluates cost, time, and quality simultaneously.
Okay, so it's the difference between telling a GPS, get me to the airport, versus saying, get me to the airport, but I want to avoid tolls, I want the most scenic route, and I need to be there in exactly 45 minutes.
Yes, perfect analogy. The agent has to optimize multiple, often conflicting variables to find the mathematically best path, not just any path.
Wow. And the pinnacle of this entire taxonomy is the learning agent. This agent does something fundamentally different. It evaluates its own performance via an internal critic and updates its procedural memory to improve future iterations.
Which is incredibly hard to do.
Right, but wait, how does an LLM do that? I thought training a model took millions of dollars in giant server farms.
Oh,
It can't just retrain its own base weights on the fly, right?
that is a great distinction to make. No, it doesn't retrain its base neural network, its semantic memory. Instead, it updates its episodic and procedural memory.
Okay.
If it tries a coding script and it fails, it analyzes the failure and writes a new instruction set into its own system prompt or episodic database that says, do not use that specific library. It causes a memory leak.
Ah,
So the next time it faces the task, its context window is loaded with the hard-won wisdom of its past failure. It alters its behavior without changing its base weights.
that makes perfect sense. Now, we know how an agent thinks, how it plans, and how it scales in complexity. But there's an elephant in the room here. If this brilliant utility-based learning agent is locked inside a server, how does it actually touch the real world? How does it interact with the outside environment to fulfill these complex goals?
This is perhaps the most impressive mechanical feat of the entire ecosystem. We have to look at the tool calling activation pipeline. It explains exactly how a language model bridges the gap between its internal thoughts and external execution.
The pipeline starts with a concept called the barrier.
Right. The barrier is the fundamental limitation of any language model. An LLM's semantic memory is frozen in time at the exact moment its initial training was completed.
Like a snapshot.
Exactly. If the model was trained in 2023, it has absolutely no idea what the stock market did this morning. It doesn't know the current weather. It doesn't know the balance of your bank account. And on its own, it cannot execute an action. It can only generate text. It is trapped behind this barrier of static knowledge and inaction.
So it hits the barrier. It realizes it lacks the information or the capability to complete the goal. To cross the barrier, it moves to the next phase, structured output.
This is translation phase, and it's highly technical. You and I communicate with the agent in natural language. We just talk to it.
Yeah.
But external systems, databases, web APIs, corporate software, they do not understand conversational English.
Right, they need code.
They crash if you send them a paragraph. They require rigid, highly structured data formats, usually JSON or XML.
JSON being JavaScript object notation, it's essentially a list of precise key value pairs, right?
Exactly. So the LLM uses its procedural memory to realize, I need to talk to the weather API. It stops generating conversational text and dynamically generates a perfectly formatted JSON object. It structures the query mathematically so the external machine can read it.
It literally shifts languages. It
Mhm.
goes from writing poetry to writing machine-readable code. Then this JSON request moves to external invocation.
The structured request is fired through an API gateway to the outside world. This is where the magic happens. The agent might invoke a web scraper to pull down an article, or trigger a Python execution environment to run a complex math formula, or query a vector database to find a specific company policy.
Let's pause on vector database because that term gets thrown around a lot in this space. How is that different from a regular database? If the agent is searching for a company policy, why does it need a vector database? Isn't it just searching for keywords?
No, and that's the brilliance of it. A traditional database uses keyword matching. If you search for vacation days, it only finds documents with those exact words. But a vector database maps information geometrically based on semantic meaning.
Geometrically, what do you mean?
It takes every document in your company and turns it into a high-dimensional vector, a coordinate in space. Documents with similar meanings are grouped closer together in that mathematical space.
So if the agent searches for time off, the vector database understands that time off is semantically located right next to vacation days and leave of absence, even if the exact keywords don't match.
Precisely. It allows the agent to retrieve information based on concepts, not just rigid strings of text. So the external tool, whether it's an API, a Python script, or a vector database, does its job and returns the result.
Which leads to the final step of the pipeline, ingestion. The external tool sends the data back, and the LLM ingests it back into its short-term memory to resume reasoning. Let's ground this in a real-world scenario from the architectural breakdown, an autonomous leave approval system.
Sure, let's walk through it. An employee, John Doe, requests 5 days off. This request hits the primary agent.
Immediately, the agent hits the barrier. It knows who John Doe is, but it has no idea how many vacation days John has left because that data is live and changing in the HR system.
Right. So, step 1, external data retrieval. The agent generates a structured JSON request, invokes the HR database API, and asks for John Doe's balance.
Yeah.
The API returns the data, John Doe balance, 10 days. The agent ingests this.
Now the agent has the context. It passes this context to step 2, the evaluation agent. This agent is assigned a specific persona, the leaver request reviewer.
This reviewer agent queries the company's vector database to retrieve the exact leave policies. It runs the logic. John is asking for 5 days. He has 10 days. 5 is less than 10. The dates requested do not fall on a company blackout period. The logic holds. The request is valid.
And finally, it moves to step 3, the execution agent. The persona here is leave approver. This agent formulates a new structured JSON output, invokes the HR system API again, and executes a command to deduct 5 days from John's balance, change the status to approved, and trigger an email notification.
The structural takeaway here is that tools break complex tasks down into modular components. The LLM is the reasoning engine, but the tools are its hands and eyes.
Think of it like a brilliant detective. The LLM is the detective. They're phenomenal at deducing motives, spotting logical inconsistencies, and building a theory of the crime. But the detective doesn't have a mass spectrometer built into their brain.
Right.
When they find a mysterious chemical at the crime scene, they hit the barrier. They can't analyze it, so they package it up perfectly, that's the structured output, and send it out to the forensics lab. The forensics lab is the external invocation.
Good analogy.
The lab runs the chemical analysis, sends the forensic report back, and the detective ingests that data. Suddenly, the detective realizes the chemical matches a factory across town, and they resume solving the case. The detective doesn't need to know how to operate the lab equipment. They just need to know how to call the lab and read the results.
That is exactly how this architecture separates cognitive reasoning from operational execution.
Okay, but this exposes a massive vulnerability. Let's say the detective misreads the lab report and arrests the wrong person. Humans make mistakes constantly. If an autonomous agent makes a mistake, say it writes a faulty Python script or hallucinates a piece of data, what prevents it from just barreling forward, executing the wrong tool, and ruining the entire system? How does it catch its own errors without a human looking over its shoulder?
This brings us to what is arguably the most critical component for true, reliable autonomy, the metacognitive engine. We are moving beyond mere cognition thinking about the task to metacognition, thinking about how the system is thinking.
Metacognition. The structural loop for this is fascinating. It's a 4-phase cycle. Phase 1 is action. The agent attempts the task, it writes the code, or drafts the email, or queries the database.
But instead of immediately delivering that output to the user, the system intercepts its own work. It drops into phase 2, the internal critic.
And how does an LLM criticize itself? Doesn't it just think whatever it generated is correct?
In a basic prompt, yes. But structurally, the system instantiates a parallel reasoning process. It essentially forks itself. The original agent-generated work, a secondary subroutine is spun up with a specific critic system prompt. This critic takes the output, places it next to the original central goal node, and rigorously scans for logic gaps, syntax errors, or hallucinated facts.
And when it finds an error, it moves to phase 3, verbal self-reflection. It actually articulates its own failure.
What's fascinating here is this is a profound quirk of how large language models function. They compute through language. By forcing the model to generate a natural language critique of its own work, what we call chain of thought reasoning, it actually forces the attention mechanism of the neural network to focus on the exact point of failure.
So it writes out its thought process.
Yes. It might generate an internal thought that says, wait, My Python script failed because I used a deprecated library for the data sorting. Also, the output format does not match the JSON schema required.
It's literally talking to itself to solve a logic puzzle. Wait, so the system is effectively talking to itself, judging its own work and correcting its own math before it hands the answer back to you.
Yes, exactly.
It's like when you are doing complicated math and you start muttering under your breath, carry the two, wait, no, I forgot to multiply the denominator. The act of verbalizing it exposes the error.
Precisely. Which leads to the final step, phase 4, state update. It takes that verbalized realization, the knowledge about the deprecated library, and loads it directly into its short-term context window. Now, the loop cycles back to phase 1. The agent attempts the code again, but this time its immediate memory contains a glaring warning about its previous mistake.
It heals itself. It debugs its own logic before you even see the final result. It transforms from a static response engine into a resilient, self-optimizing problem solver.
It's incredible. But as powerful as that loop is, it introduces a new problem. A single agent trying to execute a task, reflect on it, critique itself, and manage external tools eventually hits a wall.
Right. The architecture calls this the single agent bottleneck. Even with self-reflection, a single digital mind can only do so much.
The limitations are structural. First, you have a computational ceiling. The context window can only hold so many tokens. If the agent is trying to analyze a 500-page legal document, plan a marketing strategy, and write the code for a website, all in one massive prompt, the context window saturates.
It just forgets things.
Yeah, the attention mechanism dilutes, and the model starts forgetting earlier instructions.
It also suffers from what we might call persona collapse. If you tell one model, be an incredibly creative, out-of-the-box thinker, but also be a ruthlessly strict legal compliance officer, the prompt parameters conflict, it can't be both at the same time efficiently.
That's a great point.
It's like asking one human to be the visionary CEO, the strict lead accountant, and the HR manager all at once. They are going to drop the ball.
Which necessitates the evolutionary leap in this blueprint, moving from the individual to the ecosystem. We shift from a single agent to what Marvin Minsky famously called the society of minds.
We build a swarm. Instead of one giant brain trying to process everything, you have a network of specialized brains. But if you have dozens of autonomous agents running around, how do you prevent total chaos? How do they not just overwrite each other's work?
You enforce structure. You build an organizational hierarchy for software. The architectural diagram here literally looks like a corporate org chart. At the very top, you have the manager node.
And the manager node's job is global traffic flow. It doesn't actually do the granular work.
Exactly. The manager node receives the complex prompt from the user. Its only job is to break that massive problem down into logical chunks, figure out which specialists are needed, and delegate those chunks down the chain of command.
The tasks flow down to the execution nodes at the bottom of the chart. These are the highly constrained specialists. They receive a specific task, use their specific tools, and pass the result back up.
The benefits of this hierarchical optimization are massive. First, you get a reduction of duplicated effort. If you just have a swarm with no manager, 3 different agents might independently decide they need to scrape the same website, wasting compute time and money.
Right.
The manager node coordinates the workflow, so Agent A scrapes the data, Agent B cleans it, and Agent C summarizes it.
It also allows for true delegation. The manager node sets the overarching constraints, say, summarize this data in under 500 words, and the execution node operates with total autonomy within those constraints.
And crucially, it optimizes compute. Running state-of-the-art trillion-parameter LLMs is incredibly expensive. You do not need a genius-level model to format a CSV file.
That's true.
In this hierarchy, the manager node might be the expensive, complex model, but it routes the simple formatting task to a tiny, incredibly fast, cheap model at the bottom of the hierarchy. You optimize the cost-to-intelligence ratio of the entire system.
Okay, that covers the division of labor. But what about quality control across multiple domains? The architecture introduces another multi-agent topology called the Group Chat Manager, and this is brilliant. Imagine a digital boardroom.
The group chat manager sits at the head of the table. Surrounding it are several highly specialized personas. Let's say we were generating a social media campaign for a new financial product.
So the board members are instantiated. We have a tweet writer whose prompt makes them witty and engaging. We have an SEO reviewer who only cares about algorithm visibility and keywords. And we have a legal reviewer whose sole directive is to ensure regulatory compliance.
The manager tells the tweet writer to draft the first proposal. The tweet writer generates a catchy, aggressive post promising huge financial returns.
But the manager doesn't send that to the user. The manager hands that draft across the table to the legal reviewer. The legal reviewer's entire system architecture is designed to find flaws. It reads the draft and immediately flags it. This language implies a guaranteed return on investment, which violates SEC regulations. Reject.
The manager takes that rejection, routes it back to the tweet writer, and says, revise this, adhering to these specific legal constraints. The tweet writer tries again. This time it's compliant. Then the manager hands it to the SEO reviewer, who says, legally sound, but you missed our primary keyword. Inject it naturally.
They are essentially arguing with each other.
They are structurally incentivized to be adversarial. By forcing agents with conflicting priorities to critique each other's outputs in a shared environment, the system iteratively refines its work. The dialectic pressure drastically improves factual accuracy and quality far beyond what a single model could ever achieve. The output is rigorously pressure tested before the human ever sees it.
So we have mapped out this breathtaking architecture. We understand the memory quadrants, the tool calling via JSON, the self-reflection loops, and the hierarchical societies of mind. But let's get incredibly practical. How on earth does anyone actually build this? If a developer has to hand code every single API gateway, every reflection loop, and every conversation turn between these agents, it would take months to build a simple workflow.
This is the final piece of the puzzle, and it's why this paradigm shift is accelerating so fast. We have to look at the orchestration frameworks that are standardizing all of this. The blueprint focuses specifically on AutoGen.
AutoGen is the open source engine powering this revolution, heavily backed by Microsoft and major universities. It is the scaffolding for the multi-agent ecosystem, and it has, over 30,000 GitHub stars.
AutoGen provides the granular developer control to define these workflows without having to reinvent the wheel. You don't have to write the code for how two LLMs talk to each other. AutoGen handles the underlying infrastructure. You just define the personas and the rules of engagement.
Let's look at the fundamental building block in AutoGen, the conversible agent class. You can write a few lines of code to instantiate two agents. Let's call them Alice, an AI assistant, and Bob, a curious learner.
You give Alice a system prompt directing her to provide precise answers. You give Bob a prompt directing him to ask consecutive questions about whatever Alice says. You point them at each other and hit run. AutoGen manages the message passing, the context windows, and the API calls to the underlying LLMs automatically.
But there is a crucial safety valve built into this architecture, the max turns limit.
Yes, if you set Alice to answer and Bob to question indefinitely, they will quite literally talk forever, caught in an infinite loop, burning through thousands of dollars in API compute costs. The max turns parameter allows a developer to say you two can argue, but cut it off after 10 exchanges. It forces resolution.
But the barrier to entry is dropping even lower than writing Python scripts to instantiate Alice and Bob. The architecture introduces AutoGen Studio. This is the low-code orchestration layer.
This raises an important question about the future of human work. This is where the capability moves from software engineers to system thinkers. AutoGen Studio provides a visual drag-and-drop interface. You don't need to stare at a command line terminal.
Let's detail exactly how you use this interface, because it's the culmination of everything we've discussed. It's built on three pillars. The first is agent configuration.
In the Studio, creating an agent is essentially filling out a web form. You click New Agent, you name it Legal Reviewer. You select which underlying LLM model you want it to use. Maybe you pick a cheaper model to save money. You paste in the system prompt defining its strict legal persona. And crucially, you attach tools. You literally check a box that gives this specific agent access to a Python execution environment or the company's vector database.
The second pillar is workflow mapping. This is where you draw the topology.
You take the agents you just configured and drag them onto a digital canvas. You draw a line from the user proxy node to the manager node. You draw lines connecting the manager to the tweet writer and the legal reviewer, grouping them into a group chat topology. You are visually wiring the society of minds together.
And the third pillar is playground sessions. This is where the human on the perimeter steps in.
You type a prompt into the visual playground, write a social media post, and you hit play. You can watch the actual JSON messages passing back and forth between the nodes in real time. You watch the reflection loops trigger. And if the legal reviewer gets stuck in a logic loop, or the tweet writer hallucinates a tool call, you, the human, can pause the session, inject a natural language correction into the stream, and set the system back on track.
So, what does this all mean for the listener? The architecture clearly states that the barrier to entry is rapidly lowering, shifting the human focus from raw coding to high-level system architecture. The value is no longer in knowing the syntax of a programming language. The AI agents write the code. They call the APIs. They critique their own outputs. Your value is in systems thinking. You don't need to be a coding wizard. You need to be an excellent manager. You have to understand how to design the workflow, define the personas, and architect the ecosystem.
You are evolving from a typist of code to a choreographer of digital labor.
This entire deep dive has covered massive ground. Let's synthesize the core takeaways. First, the fundamental user experience is moving from static, deterministic menus to dynamic, probabilistic goal fulfillment engines. The era of manual clicking is ending.
Second, the single model bottleneck has officially been broken. We are no longer relying on one giant unwieldy brain. We are building collaborative, hierarchical societies of specialized minds capable of reflection and peer review.
And third, architecture overtakes explicit coding as the primary discipline. Frameworks like AutoGen make orchestration accessible to anyone who can think logically about systems. Sonia Huang from Sequoia Capital summarized this perfectly in the source. One of our core beliefs is that agents are the next big wave of AI, and that we're moving as an industry from co-pilots to agents.
A co-pilot sits beside you and suggests a sentence while you write the email. An agent understands your intent, pulls data from the vector database, drafts the email, gets it reviewed by a compliance agent, and sends it, all while you are focused on higher-level strategy.
This fundamentally alters your relationship with technology. You're going to do far less clicking and far more delegating. But I want to leave you with a final thought to mull over. If architecture overtakes coding, and these agents are executing the tools, writing the JSON requests, and even acting as the fierce critics of their own work,
Right.
what ultimately happens to your role? We are rapidly shifting from being the active creators of digital actions to being the governors of autonomous digital societies. You are no longer driving the manual transmission car. You are managing a fleet of autonomous taxis. The software is learning to operate without your constant input. The question you have to answer is, are you ready to step back from the keyboard and learn how to manage a workforce of machines?